Hello, I hope all of you are doing fine. In today's session, we will look into another aspect in the dynamics, which is called as the dynamic balancing. Now, this is also a very important aspect in the design. Now, as we know, a machine. What is a machine? Machine is an assemblage of various components to do useful work or to get desired work. Now, when we are saying with the help of various design fundamentals and kinematic analysis, we determine the dimensions of these various components involved, their cross sections and all, and then we assemble them together. So intention of say if this is a mechanical system, so this is a mechanical system. So the intention of this mechanical system is to get desired work. So the intentions are to get the desired work, and another aspect is that it should run smoothly. So that means when it is running, there should not be any disturbances or vibrations while it is working. Now, these assemblage of or the machine or the mechanical system, you can say, we place it when we are installing it on the support. Right? Now, say this is comprising of so many components together, so they are having their own mass, so it will be having its own weight. Now, in this condition, if you see, when we are placing it on the supports, so the support is quite comfortably reacting or providing the reaction to this loading, and the system is stable. So, here in this situation, the load, whatever is acting, it is not changing with respect to time. So when it is not changing with respect to time, so there are no unbalanced forces in the system. Right? Now let us consider one component in this system. So what is happening when the system is running? Now when the system is running, the components they have relative motion. So let us consider one component, and let us say the center of mass is at G, and it is having certain velocity, which is a linear velocity, is having a linear velocity, as well as it has some angular velocity omega. So what will be the linear momentum? The linear momentum will be equal to the mass. Let us say it is having some mass m, so mass into the velocity. Now there is not only a single component, there are so many other components also in the system. So the total linear momentum, I can say the total linear momentum will be summation of all the masses and their respective velocities. Say from 1 to, let us say there are n components in the system. Another thing will be when it is having an angular velocity, so it will be having some angular momentum, which will be in that case I, where I is the mass moment of inertia at the center of mass, into the omega, and similarly this total angular momentum will be sum of this I into omega, where I from having n components. So now if this is constant, if this remains constant, then there will be no inertia force in the system, because we know the rate of change of momentum will introduce a force in the system, which is called as the inertia force, and it is evident, and we know these components which are there in a machine or a mechanism, these values, the velocities and angular velocities, they are changing, they do have change. So that means whatever this inertia force will be, that will be the rate of change of the linear momentum, and we can say which is equal to the mass into the acceleration, or I can say the summation, right? And similarly, a moment will be there in the system which will be the rate of change of angular momentum, so which is, I can say, I into alpha. So when we are differentiating, so we are getting these as the magnitude of the force and the momentum, and these are the inertia forces and inertia moment coming into the system, and they are changing with respect to time. So they are creating trouble as these values are continuously changing. So it is giving, they are getting introduced in the system. So they are creating this trouble, and if I want to nullify or neutralize this, so I need to introduce a force of same magnitude in the system, but which will be of opposite nature to it, as well as the moment. So that means if I am not providing this, the system is going to be into a state of an unbalance, and lot of vibrations and will be there, and as I've said, the system will not be running smoothly. So to make it run, then I'll have to introduce these forces in the system. So that means if the summation of these inertia forces and inertia moment, if these are zero, if I make it zero, then I can say that the system is dynamically balanced, or this will be called as the dynamic balancing of the system. This is a very important aspect. Now what happens is, many times, most of the times, like we are designing all the components and all, we know what is going to happen, so we are trying to take care of all these things at the design level only. But when we install the machine at a particular place and when we run, we see that these vibrations are there in the system. Now why this can be happening? One of the reason can be the errors involved while assembling all the components together, which will create, or due to which there can be certain eccentricities in the system, or maybe due to the deformation if the components are quite heavy. So in that case, deformations will be there. So let us say if there is a shaft and it is and the shaft is and various heavy components are mounted on the shaft, so obviously there is going to be deformation of the shaft, and when such a shaft is running at very high speeds, so these inertia forces will be coming into the system. So that is how then we have to look into the system and try to take care or balance the system so that the system runs smoothly. Now here let us try to again understand with the help of, now most of our mechanical systems do have a slider crank mechanism. This is one of the best examples where we can understand. Now if you see the motion of all these three components in this mechanism, out of which this is the crank, which is a pure rotating member, right? And here if you see the slider is a pure translating member. And here if you see the connecting rod, which is also called as a floating link, it is having a combined motion. That means it is rotating as well as it is having a linear motion. So while balancing, we take care of first the disturbing rotating masses. That means we go for the balancing of rotating masses. Then we think of the situation for balancing the reciprocating masses, and then as a whole, wherever the combined motions are there, the balancing of the entire mechanism. Step by step, we balance the system. Now what happens, as I said, we see that when we are doing the balancing at the designing stage, that is one aspect. And second aspect, as I said, when we install a particular machine at a particular location, due to these assembly errors and all, we find out that there is unbalance in the system, and we experience lot of unsmooth functioning of, so lot of vibrations in the system. So when we are doing the balancing after the installation of the system, which is done, so that balancing is called as the field balancing. So let us try to understand one by one how we are balancing these systems. So in which the first we will see balancing of the rotating masses. So let us say there is a shaft on which it is supported at the bearing. Now this can be of a regular shape or can be an irregular shape, whatever may be the condition, but I cannot assure that the center of the mass of this disc is lying at the geometric center. As theoretically, if I see, if it is a circular disc, the center of mass is supposed to be at the center of the disc. But for a component, we cannot assure that this mass is really lying at the geometric center. Now it might, or it will, chances are there that it is lying somewhere eccentric or away from its axis of rotation. Let us say this distance is at a distance E from the, so it is having some mass which is concentrated eccentric to the center of rotation of the axis. So what kind of dynamic force is expected to be introduced in the system? Now pictorially, if we want to show, say this is the shaft, or maybe in another way we can show, and say the mass is concentrated at the eccentricity m, so maybe in this fashion, and this shaft is rotating at some angular velocity omega. So when this shaft is rotating at certain angular velocity omega and the mass is concentrated eccentric to the center of rotation, then in that case a dynamic force which will be equal to the magnitude of the centrifugal force will be acting or will get introduced in the system. And this centrifugal force at this instant, if we say, it will be acting radially outward. So let us say this is some force F which is acting radially outward. So what will be the magnitude of this forces? So this will be this mass, radius of rotation, omega square. So this will be the magnitude of this force which will get introduced when the system is running. Now this force is such that you can see when it is rotating, that means this force is continuously changing its direction. So this is a dynamic force which is continuously changing with respect to time, and hence it is creating the dynamic unbalance in the system. Now how I can neutralize or nullify this unbalanced force in the system? It's very simple. If I can provide a force which is exactly opposite to this force and is of the same nature of this force, then this unbalanced force can be neutralized or nullified from the system. So how I can do that? So very simple can be, I can provide a mass exactly opposite to it, which I'll call as a balancing mass, and at certain radius, let us say RB, and I want the magnitude of this force should be same as this. So it should give a force, or it should introduce a force which I'll call as the balancing force, whose magnitude should be exactly equal to this disturbing force. So I want this FB balancing force to be equal to this force. So I can say again, when I am placing this mass same on the same shaft, let us say if it is acting here, so maybe I put a mass on this disc, right, which is a balancing mass, and at some radius which is concentrated at some radius B on the same disc itself, on the same plane and exactly opposite to it. So this phase opposition is of 180 degrees. I am placing it exactly opposite to it. So when the disc is rotating, so when this mass is at a position, every time this balancing mass will be exactly opposite to the disturbing force, and this is also rotating on the same shaft. So magnitude of this force will be equal to the balancing mass, or I can say will be equal to, or I can then determine what should be this balancing mass which I can place at maybe a pre-decided radius, or maybe whatever is the condition based on which I can place that mass here, so that the sum of these forces comes out to be 0. So as we see here, so I place this balancing mass at a radius this, so that is how then I am balancing this system. Now maybe due to the restrictions or the physical constraint, you can say, of the system, maybe it's not possible for me to maybe provide a single mass. Like you can see here the relation, I can increase the radius so that I can reduce this mass, because when I am placing an extra mass on this system, I am increasing the bulk of that system, right? So if it is, let us say, if this is 10 kg and radius is some, say, unit 1, so the force will be 10. So for that also again I will be requiring a mass of 10 to be placed here. So overall, if you see, the total load on this system becomes 20, right? So maybe due to this, if I want to reduce this value of the balancing mass, what I can do is I can increase the radius value, so that the mass which I need to add on the system, if I am doing field balancing, as I have already said, when we are doing field balancing, when the entire system is assembled and installed, and when we check it for smooth running, we find out there is a vibration. So we add these additional masses in the system then and there itself. So that means in that case we will be increasing the bulk or the total mass in the system if these values are too great. So if I want to reduce this mass, what I can do is I can increase the radius, right? But as well, I have a limitation. If it is a disc, at the most I can place this mass at the circumference of this disc. So there is a limitation for this radius of the balancing mass. So in that case, what I can do? Now before moving into that aspect, it is ultimately what we are seeing. So let us take this same example So there is this shaft which is having unbalance of mass m at, let us say now, say at radius r. So first option or first condition, we have seen that I can place this mass, balancing mass, at radius rb, and the situation is taken care of. The system is completely balanced. Now, what I want the summation of these forces. That means summation of to be 0. When this is 0, we are saying that the system is balanced. Now let us say in the same case, I have another option. If this is the disturbing mass m at radius r, I have another option. I am placing the balancing mass maybe somewhere else. I select another plane of rotation where I am placing this balancing mass at some radius, and we are ensuring that this force, disturbing force and the balancing force, this summation is again 0. So if this is the case, the system is definitely balanced. But when we run such a system, we see that still when such a system runs, there is a lot of vibration in the system. Now what might be the cause of this vibration? Now here if you see, the summation of these forces is certainly coming out to be 0. Now this situation is called as static balancing. Now how we can check for static balancing? Let me show you how this situation can be. So if there is this disk which is having the mass concentration somewhere here, so this is the center of mass with radius r. So what I am doing is, I am placing another mass exactly opposite. So phase opposition is of 180 degree, and this is the balancing mass, but I am placing it somewhere else on the shaft than this plane of rotation with radius r. So if you see, it is in phase opposition, so the summation of these forces, they are coming out to be, it is coming out to be 0. But in the process, what is happening is, why there will be vibration in the system or unbalance in the system will be, when this is one force which is acting opposite to this force, so this is going to create a couple, because they are, let us say, at a distance a. So this force into a, because the magnitude of these two forces will be same, which are separated by a distance a. So it is going to create a couple, and this couple, the plane of rotation of this couple is also continuously changing as this shaft is rotating at omega. So there is a moment. So if I take a reference plane, so moment due to this mass and moment due to this mass, they will be acting opposite to it. They will be acting with different magnitude, and their direction is continuously changing, and hence there will be a disturbance or unbalance in the system. So when only the forces are balanced, when the summation of these forces is 0, the system is, this is called as the static balancing. Now how we can check static balancing? So if there are just there is a disc which is mounted on a shaft, and the shaft is supported by free bearing, and we have placed this balancing mass. So when we rotate, it will stop at random positions every time. Now if it is statically not balanced, then it will always come and stop at the same position. So that is how we can check for static balancing. So when the summation of forces is 0, then the system is statically balanced. Now if I want the system to be in complete dynamic balance, or if I want to have the dynamic balancing of the system, then I need to have the summation of this moments also to be equal to 0. When these two conditions are satisfied, we call this to be as dynamic balancing. So we have to ensure for dynamic balancing that the summation of forces is 0, as well as the summation of moments is also 0. Now let us see another aspect in this case, as I have shown this. Now here we have balanced the system with the help of a single mass. Now even here I can, as I have talked about the restrictions, that maybe it is not possible to place only a single mass. So I can select two different masses at two different locations. So let us say balancing mass 1 and this is balancing mass 2, such that, so it is giving F1 and F2, and say this is at R1, this is at R2. So we want this mR omega square to be mv1 R1 omega square plus mv2 R2 omega square. So again, when it is mounted on the same shaft, so we want these forces, or this is F1 plus F2, or summation of these forces to be equal to 0. So if the summation of these forces is 0, then the system is statically balanced. But here again you will see that the moment due to these two forces, now if I select this as the reference plane and say these are the distances, say L1, say this is L and this is L2 from a reference plane, the moment due to all these three forces need to be, their summation needs to be 0. When we are able to make that to be 0, then only we can say that the system is dynamically balanced. So this is as far as a single mass is concerned, but in actual conditions we can say that there are various components as well. So maybe there is a shaft on which there is a gear, there is a flywheel, and there are other components for transmission system which are mounted on the same shaft. So there can be different masses mounted on a shaft. So pictorially we see, so this is a shaft. So maybe these are, say, M1, M2 and M3. There are three different masses, but their planes of rotations are different. And now I want to balance such a system, and the end view, if you see, so maybe this is M1, this is somewhere M3, and say this is, say, M2. Now when this at different radii, R1, this is R3 and this is R2. So in this case, what will be happening when this is turning at an angular velocity? The centrifugal forces due to these will be acting radially outward. So this is, say, F1, F2, F3, and this is F2. So in that case, how I can balance this system. So as we have seen again in this case, in the earlier case, it is not necessary that we balance the entire system only with the help of a single mass, but rather we can use number of masses as well. At maximum usually we take two, consider two masses or two different reference plane of rotations on which we can place the balancing masses and balance the entire system. So as if you see, say this is this shaft, this is M1, this is somewhere here is M2, and this is somewhere here is M3 at phase whatever are there. So the force due to this will be F1, this is M2, the force is F2, and this is F3 which is due to M3. So here what we do is we select so two reference planes, right? I'll extend it just to so this is one plane and this is another plane which we have selected, any two planes, and we can balance this entire system as if by superimposing these forces on the reference planes. Like this F1 can be taken care of with the help of two forces which is acting exactly opposite to this. So maybe this and this on these reference planes. Similarly, for F3 it is acting this way, so maybe this and this in opposition with F3, and for M2 so it is in this direction, so this and this. So as if we are nullifying these forces by introducing these forces in the system at selected plane of rotations, and we can completely balance this system. Now we can get the solution with the there are two approaches. One is the graphical solution and the other is the analytical solution, out of which we will first prefer to get into, we will try to understand the graphical solution, wherein we will be superimposing all these forces on the reference planes, right? And as we can have the forces, so we can draw the vector diagrams for these forces. So this will, if we consider the unbalances, so to we can find out what is the resultant direction of this unbalanced force, and exactly opposite to the opposite to this resultant unbalanced force will be the balancing force, as well as the moments due to all these forces. We will ensure that the summation of forces is 0 and summation of moments is 0, so that the system gets balanced. So in the solutions, graphical solution or analytical solution, with respect to the given situation, we will try to, or we will determine what will be the required balancing masses at the reference planes which we will select, and we will see that rotating unbalance due to the rotating masses can be completely balanced. So that is all for this session. So in the coming session we will look into getting the solution with the help of graphical approach.